Greetings everyone. In this video, I'm going to provide an overview of multiple linear regression. The goal is to help you gain a conceptual understanding of this statistical procedure. Multiple linear regression is named as such because it involves multiple independent variables, all of which must have a linear relationship with the dependent variable. Compared to other procedures covered this semester, multiple regression is one of the most commonly used techniques in observational studies. Therefore, in this introduction, we will approach the procedure from a researcher's perspective. If you are conducting a study using multiple regression, the first step is to identify the dependent and independent variables based on your research questions and related literature. The dependent variable should be measured on either a ratio or interval scale, as it represents the outcome variable you're predicting. This is why it's also referred to as the predicted or criterion variable. The selection of independent variables should be supported by either theoretical or empirical evidence. Ideally, independent variables are continuous, though they may also be dichotomous. It's important that the independent variables are strongly correlated with the dependent variable while having low correlations among themselves. A common question is how many independent variables should be included in the regression model. Beyond theoretical considerations, you should strike a balance between simplicity and effectiveness. A model with too many independent variables may be overly complex and difficult to interpret, while a model with too few variables may lack predictive power. Finding a balance between these extremes is crucial when developing your regression model. Once you decide on the model structure, the next step is data collection. Ensure that participants are selected independently and that the sample size is sufficiently large. Multiple regression is a parametric statistical procedure that requires a large enough sample to ensure statistical power. A general rule of thumb is to have at least 20 observations per independent variable. For example, if you have 3 independent variables, the minimum recommended sample size is 60, given that 20 times 3 is 60. Larger sample size would be necessary when more independent variables are included. Step 3 involves preparing your data for analysis, including handling missing data and formatting variables correctly. Once the data is ready, step 4 is running the analysis in SPSS. I have demonstrated the steps to conduct multiple regression in SPSS in a separate tutorial. You may want to pause this video, watch that tutorial, and then return here to continue. Without repeating the details of running the analysis, I would like to highlight a few key points. First, like simple regression, multiple regression relies on ordinary least square estimation. The OLS method minimizes the differences between the observed and the predicted Y values. The SPSS output provides regression coefficients and regression constant. But before reporting the regression equations, you must first evaluate the model's effectiveness. It's essential for you to understand a few key concepts here. The regression equations show that the predicted Y is a linear combination of all independent variables. The correlation between observed and predicted y values is called the multiple correlation coefficient, denoted by a capital R. The squared value of R, known as the coefficient of determination, represents the proportion of variance in y explained by the independent variables. The ANOVA table in the SPSS output provides an F-test to determine whether R-squared is significantly different from 0. If the p-value is lower than the alpha level, you reject the null hypothesis and conclude that the independent variables collectively explain a significant amount of variance in the dependent variable. If R-squared is not statistically significant, the model does not meaningfully explain the variance, and further analysis would be pointless. If the overall regression model is significant, the next step is to test the significance of each independent variable. This involves a t-test for regression coefficients, which is included in the coefficients table in the SPSS output. The null hypothesis states that a regression coefficient is not significantly different from 0. If the p-value for an independent variable is below the alpha level, that variable significantly contributes to predicting y while controlling for all other variables in the model. Another important concept is the relative importance of independent variables. SPSS provides regression coefficients in two formats: unstandardized and standardized. Unstandardized coefficients depends on the scale of the variables, making them unsuitable for direct comparison. For example, if the first independent variable x1 represents GRE scores ranging from 100 to 800 points, and the second independent variable x2 represents student age ranging from 10 to 25 years old, their regression coefficients may differ significantly in value, even if both variables have comparable associations with the dependent variable. Specifically, the regression coefficient of x1 would be much larger than that of x2 due to the differences in their scales. Standardized regression coefficients, on the other hand, allow for comparisons because all variables are transformed to have a mean of 0 and a standard deviation of 1. The absolute values of standardized regression coefficients indicate the relative importance of independent variables, with larger values reflecting stronger contributions to the dependent variable. Effect size is another crucial aspect. In multiple regression, R-squared serves as an indicator of the model's effect size. Standardized regression coefficients represent the effect sizes of individual independent variables. After completing the analysis, use the SPSS output to write your regression equations. In both unstandardized and standardized regression equations, remember to place a hat over the predicted values. It is also important that you are able to interpret the regression coefficients correctly. The unstandardized regression coefficient represents the predicted change in the dependent variable for a 1-unit increase in the corresponding independent variable, holding all other variables constant. the standardized regression coefficient, represent the predicted change in y in standard deviation unit for a 1 standard deviation increase in the independent variable, holding all other variables constant. Interpreting regression results is not the final step. You must also ensure that the model meets its underlying assumptions and does not suffer from multicollinearity. Last week, we discussed 4 key regression assumptions. Linearity can be assessed using scatter plots, which are useful only for continuous independent variables. If an independent variable is dichotomous, a scatter plot would not be appropriate. Normality can be assessed by examining the distribution of residuals or using a PP plot. If residuals follow a normal distribution, it supports the assumption of normality. Homoscedasticity refers to constant variance in residual across all levels of independent variables, which can be checked by plotting residuals against predicted y values. A residual plot should show randomly scattered points around the horizontal line at 0 without patterns. Independence is ensured through appropriate sampling method, as we previously discussed. A common issue in multiple regression is multicollinearity, which arises when some independent variables are highly correlated with each other. This can lead to unstable regression coefficient estimates. To detect multicollinearity, examine the variance inflation factor, VIF, values in the SPSS output. A model is generally considered free of multicollinearity when all VIF values are below 10. If any independent variables have VIF values above 10, possible solutions include: number 1, removing one or more highly correlated variables. Number 2, combining highly correlated variables by computing their mean or sum if conceptually appropriate. Number 3, using advanced techniques like structural equation modeling, which is beyond the scope of this course. Another issue in multiple regression is the incorrect handling of multi-level categorical variables. For example, if racial background is coded as 1 for white, 2 for black, and 3 for other minorities, SPSS would interpret these as numeric values rather than categorical labels. To correctly include categorical variables, you must recode them into dummy variables. I have demonstrated this procedure in a separate video tutorial. Finally, be aware that multiple regression analysis can be performed using different methods, including backward selection, forward selection, and stepwise selection of independent variables. These methods apply slightly different criteria to remove independent variables that do not significantly contribute to predicting the dependent variable. However, caution is needed when using those data-driven procedures, as prediction is not the sole purpose of multiple regression. If your study is theory-driven, you may choose to include non-significant variables based on theoretical or conceptual considerations. I encourage you to explore the linked videos for more details on those methods. Additionally, understanding the difference between partial correlation and part correlation is necessary, as these concepts distinguish multiple regression from simple regression. Thank you for watching, and I hope this video helps your understanding of multiple regression.